Hi, I'm Omar, creator of the Dragon Debugger, and this is a tutorial on debugging a real-world Linux kernel crash using Dragon. We're going to go step by step through finding the root cause of a real kernel bug, focusing on Dragon's features for stack traces, local variables, and identifying unknown addresses. I've provided a core dump of this crash that you can download to follow along. If you're not familiar with Dragon's basic concepts, I recommend reading the Dragon user guide or watching my talk at Kernel Recipes 2022 titled Powerful and Programmable Kernel Debugging with Dragon. I'll link to both below. Let's get started. To get set up, you're going to need to do three things: install Dragon, download the core dump and debugging symbols, and check out the Linux 6.11 source code. The written version of this tutorial has details for doing all of those. That's also linked below, so go follow the setup steps there, which is what I've already done. On the right, I have the core dump and debugging symbols file, and on the left, I have the Linux source code checkout. Now, run Dragon with the -c flag to specify the name of the core dump, VM core in this case, and the -s flag to specify the name of the debugging symbols file, VM Linux. Since we only care about the main kernel for this bug and not any kernel modules, also add --main symbols. When you run that, it'll drop you into an interactive Python shell with all of Dragon's functionality loaded. To give some background before we jump in, this was a real crash that we encountered in production on multiple kernel versions, including the latest version at the time, 6.11. It was mostly happening on storage-heavy workloads. Based on the kernel logs, the crashes seem to be related to the block layer, which is the part of the kernel responsible for disk I/O. So let's start by looking at the kernel logs. Dragon has a helper for dumping the kernel logs named printdmessage. Go ahead and call it. This is what the kernel log during the crash. Scroll up and find the line starting with bug. This line tells us that the kernel crashed because it dereferenced a null pointer and accessed the invalid address 6fc. A few lines below that is the exact instruction pointer where the crash happened in this raw spinlock IRQ save function. Below that is a CPU register dump, and further down is a stack trace. From the stack trace, we can see that we got an interrupt for an I/O completion, which called into the block layer, tried to wake something up, before ultimately crashing in raw spinlock IRQ save. Note that you should usually ignore these lines starting with a question mark. Those are still function addresses on the stack that aren't actually part of the stack trace. Now let's look at Dragon's view of the stack trace. We're going to use it a lot, so assign it to a variable by doing trace equals. Then, to get the stack trace of the thread that caused the crash, call prog.crashedThread.stacktrace. Then print it. Notice that this shows some information that's not in the kernel logs. It includes file names and line and column numbers for each stack frame, and it includes inline function calls. For example, these first few functions don't appear in the kernel logs because they're all inlined. You can get more information about an individual stack frame by indexing into the stack trace. Let's look at frame 3. This confirms that queued spinlock was inlined into raw spinlock IRQ save. Now let's find where the null pointer came from by looking at local variables. The first three functions in the stack trace implement an atomic compare exchange operation. That's basically a fancy memory access, so I'm going to skip over them and start at frame 3, which is queued spinlock. Let's look at the source code for it. Dragon tells us where exactly it is, so in your Linux checkout, open include asm generic qspinlock.h and jump to line 111. And this is the line where the crash happened. Notice that it's accessing this pointer, lock, which is a function parameter. Let's look at its value. In Dragon, you can access function parameters and local variables by indexing into a stack frame. So back in Dragon, we want frame 3, and the variable name lock. Print that. And this matches the address we saw in the kernel logs earlier. Let's figure out where this lock came from. The next few stack frames, 4 through 7, are all still in the spinlock implementation. We could pull up the source code for each of them, but I'm going to take an educated guess that they all use the same parameter name. We can easily check that by repeating what we just did in each frame. So in frame 4, and that matches. Frame 5 matches. Frame 6 matches. And frame 7. So frame 7 doesn't have a variable named lock. Let's pull up the source code for it. So the function is called class raw spinlock IRQ save constructor, and it's an include linux spinlock.h at line 551. It looks like this function is generated by a macro. We could try and figure out what the macro expands to, but I'm going to show you a trick in drgn instead. You can get the list of all parameters and local variables visible in a stack frame by calling .locals on that frame. So we want frame 7, .locals. This means that there are variables named L and _t. L could mean lock, so let's try that. And yep, it matches. Frame 8 is in try to wake up, which is finally out of the spin lock implementation. So it must be who is actually trying to acquire the lock. Let's open the code, kernel sked core.c at line 4051. This line is acquiring this lock, PI lock, which is a member in P, and P is a parameter. It's a task struct, which is a representation of a thread. Let's look at it in drgn. Frame 8, variable P, and there's our null pointer. So where did 6fc come from? Well, PI lock is a member of task struct. drgn has a helper offset of, which takes a type. We want struct task struct and a member name. And it returns the offset of that member in that type. Let's print it in hex. That's where 6fc came from. drgn also has a helper for doing the inverse, member at offset, which also takes a type and an offset. And it returns the name of the member at that offset. Spin locks are implemented using a union, so that's where these ORs come from, but it's definitely in PI lock. Let's keep going to find where P came from. The next frame, frame 9, is an rqqs wake function, which is in block rqqs.c at line 223. This is passing data arrow task to wake up process. Wake up process is just a wrapper around try to wake up that got optimized out. So let's print data. So task isn't null here. Let's see what task it is then. Task struct has a member named com, which is a thread name. Print that by adding .task.com. That's empty, which isn't supposed to happen. This means that this might not be a valid task struct pointer. So if it's not null and it's not valid, then what is it? drgn has a helper named identify address. That takes an address and figures out what it refers to. We want the task pointer. So it's not a task struct at all. It's a completely unrelated type. Let's also check data itself. This means that data is on the stack of the thread with PID 909 named FIO. Okay, notice that we've seen 3 possibilities for data arrow task. When it was passed to the wake up process, it was a null pointer. By the time of the crash, it was a completely unrelated pointer. And it's supposed to be a valid task pointer. This all suggests that there's some sort of race condition on data arrow task. Now let's see where data comes from. Scroll up in rqqs wake function and see that data comes from cur, which is a wait queue entry parameter. Search for rqqs wait data in this same file to see who creates the wait queue entry. You should find this function, rqqs wait. rqqs wait creates a data variable on its stack, and it sets task to the currently running task. Then it tries to get something called an in-flight counter. You don't need to know what that is, but if it fails, then it puts itself on a wait queue, which is what prepare to wait exclusive does. Then it goes into this loop where it tries to acquire an in-flight counter. If that fails, it goes to sleep. And then when it wakes up, it tries again until it succeeds, at which point it calls finish wait to remove itself from the wait queue if needed. Since data was on the stack of PID 909, we'd expect that PID 909 is currently in rqqs wait. Check that in drgn by calling stack trace with the PID. It's not in rqqs wait. It seems to be doing something else now. Let's take a step back to analyze what we found. PID 909 was the waiter in this situation, and the thread that crashed was the waker. The waiter must have gotten an in-flight token and moved on. The waker must have found the waiter's data in the small window when it was on the wait queue. But by the time the waker called wake up process, the waiter had moved on and reused its stack memory for something else. Wakers and waiters are supposed to be synchronized, so something went wrong here. Go back to the crashing stack trace, and notice that rqqos wake function is called via this wakeup common lock function. Open the code for that in kernel sched-wait.c at line 106, and notice that it's holding this lock on the wait queue head. On the waiter side, finish wait, which is in the same file, takes that same lock here. But there's an important detail here. Finish wait doesn't take the lock if the wait queue list entry is empty. In other words, if the entry has already been removed from the wait queue, then it returns immediately. Now go back to rqqos wake function. It deletes the wait queue entry, which removes it from the wait queue, and then it accesses the entry. Remember that data is part of the entry. And that's the race condition. As soon as the entry has been removed from the wait queue, the waiter is free to move on without synchronizing. The fix is actually really easy. Instead of deleting the entry first, delete it last. This also needs to use the careful variant of list deletion for memory ordering reasons. And that's the exact fix that was merged in Linux 6.12. And that's the end-to-end process of debugging a kernel crash. Obviously, this is just one bug, and different bugs need different techniques. We mainly relied on stack traces for this bug, but some other investigations need to use more drg helpers, for example. Debugging is also not usually a straight path like I presented here. You'll normally need to try a lot of things before finding the right explanation. That's where Dragon's programmability comes in handy. The main things I hope you take away from this are the general strategy for debugging, as well as a few specific Dragon tricks. Identify address is one of my favorite Dragon helpers, and stackframe.locals and member@offset are also really useful. Since you already have this core dump open, pull up the Dragon helpers documentation and poke around and see what else you can find. The written version of this tutorial has a bonus challenge where you use a few Dragon helpers to find the script that I ran to reproduce this bug, so try that out if you want. Thanks for watching.